Well, Chris is good too, though. He was.
Trying to make my money, man.
They already weaned him off his crutches.
Yeah.
He's just got
So,
They didn't write this batch up to make it.
What did he tell you what was wrong with him?
Motion.
Because he was telling people what he was like, fully tolerant, like, okay, it's fully tolerant to surgery.
Combination of linear.
He does have a tear, but it's already like actively healed. He had a
We're
small
working our
tear.
way up
He
to.
had a small tear there, a
the
small tear in his meniscus, but it's already healing itself.
done for
So
annular.
he's fine.
So we were talking about banked versus unbanked curves. Again, you imagine you have a curve that's like flat on the ground.
That's fine.
There's some object going around the curve. So then what did we say last time? What causes the centripetal acceleration on this one? Yeah, static friction. It's what's keeping your object moving in a circle. Now, here's a question. When I see a banked curve, where do you think where's an example where you'd see a banked curve? Racetrack. Do you think it's friction that keeps you, keep your acceleration radial? No. Take a look at this. So,
Oh, you guys are serious.
Why are you mad?
you
I
now,
don't want to see my, it's not like I don't want to see my sister, it's just.
you now have a, I don't know, again, like a racetrack, and you're going around it, it's slightly, it's tilted at an angle. So you can have your same object on here.
She got like in the 91 percentile in her family medicine or internal medicine test.
Okay, so
Like,
we want to think about how to analyze this, okay? So which way is the centripetal acceleration going to point?
that way,
So is it going to be at an angle, or is it going to be?
at an angle that way.
I think it's at an angle.
Maybe not
No, it
straight.
is.
Yeah, so your acceleration is still going to be horizontal. So we have to figure out how to figure that, what that means. So your acceleration. The radial acceleration is still going to be horizontal. So you remember before when we were looking at objects sliding down a slope, the acceleration was down the track. But again, this time you're just worried about staying in a circle. So that acceleration is going to be horizontal towards the center of the circle. And then how do we figure that out? Okay, so we remember. We still have that. But now, there's your normal force. Take a look at this.
I don't understand that.
So that's your theta in there.
Just trying to figure out. No, I'm not my sister. She'll tell me.
This time we're keeping our X and Y directions. We're not rotating it. We're keeping them standard. Now, you remember before when we were looking at this. And what our normal force would be, yeah. Remember we had that when we were looking at objects sliding down a track? Do you think this normal force is the same as that normal force? No, it's not. It's actually going to be larger. Why do you think it's going to be larger? Well, I mean, so we still have the weight of the object causing part of the normal force. What do you think is causing the other part? Yes, there's going to be a centrifugal acceleration. So you can think that there's going to be another force pointing that way, pushing your, like, I guess your car into the track, which causes it to press back harder. This normal force is going to be larger. We're not really going to calculate that, but just know that these two normal forces are not the same. So if you're solving a problem with an object going around a banked slope, you want to make sure you're using the components of the normal force, not your mg cosine theta. That's only part of that normal
So
force.
this is a banked curve?
Yes.
I like parameters.
And then, of course, your normal force, not that one, is going to be you're going to have to think of this in the component form. And you can find its magnitude, of course, by your x squared plus your y squared and square root of the whole thing. Okay. So again, here we have a car going around a banked curve that's that has a bank of 4 degrees. It's covered in ice. The car is moving at 11 meters per second. What is the safest speed to go around the curve with a radius of curvature of 25 meters? So basically, again, you know that centrifugal force that's pushing out? It's also going to have components based off the bank of this curve. And if you start going too fast, your car is going to start sliding up the curve until you fly off the edge.
So ideally, when we need the weight of the car to the amount of friction present, so
Eventually, yes. And there's no friction, it's ice.
we can just predict that car is no longer going to be on that curve.
No, there is a speed that you can go, where the centrifugal acceleration just due to the normal force will keep you on the track. Because remember, if there's no ice, if there's ice and there's no friction, your car is also, if you just stopped, it would slide down the track.
So there's an element of gravitational
Uh-huh.
force too.
Yeah,
No one else.
It goes back to the waste.
Yep. It's going to be in there, yes. So let's draw a diagram. Yeah, I know it's a lot larger than 4 degrees. Try to draw 4 degrees. It's not easy. Okay, so that's going around the track. It is 4 degrees. I said positive x the other way because I want my centripetal acceleration to be positive. It's just, it's not necessary. It's just one of my little neurotic things.
I think she did. She did all.
Yeah, let's start looking at the forces that we have.
I mean, that's not.
We're gonna have the weight of the car. Normal force. We X and Y components, and then theta in there. Now, your centripetal acceleration, of course, would be going to be that way. So yeah, there is going to be a balance. It's going to keep your car going around the track. It's not going to be going so fast it slides up the track and off. It's not going to be going so slow it slides down the track. We want to know what that speed is. Okay, so let's just start with, well, I'm going to go ahead and write these down. We'll use those. Okay, so the first thing I'm going to do is I'm going to look at my forces in each direction. Do you remember your definition of centripetal acceleration? You know, I have always appreciated that you're honest. It's been several years now. Do you remember this? Nope, not at all. Remember, you can plug in some of your definitions. You know, we're trying to solve for this speed. We need something with speed in it. So our centripetal acceleration is going to be v squared over r. Okay, one of them is an equilibrium expression, one of them isn't. What's the difference?
One set zero.
So why is the y direction in equilibrium? Yeah, it's not moving in the up or down direction. The x component, of course, is not in equilibrium because just for the fact that you're moving in a circle, you have to have a centripetal acceleration. Okay, so now one of the things we don't know, now we know we can't use like mg cosine of theta to find the normal force. So we do not have a number for that normal force. What's one of the tricks we've been using to get rid of the variable we don't, that we can't figure out? That's going to give me n squared. It's just going to square the thing I don't know. What? Well, I mean, we can do calculus if you want. What do we do when we want to, like, think about in chemistry when you were, translating from one set of units to another? How do you get rid of the units you don't want? How? You divide them. So let's divide these two. Then that's going to give us mv squared over r over mg. Mass is going to go away. We end up with the speed we're looking for squared over gravity times r. You also notice that the n cancels itself out. Now, let's reach back to our trigonometry days. What is sine over cosine? Tangent. So
Just put the tangent of that.
theta e squared over gr. Dr tangent theta. And then, of course, your velocity that you're looking for, your speed. Square root of that whole thing. And plug in numbers. What was the radius? Yep, 25 meters. And we end up with a velocity. Which, if you're in a car, is really slow. Do any of the athletes run about 4 meters per second? A horse could do it. Yeah, so this is a. But you notice something. So what did you notice about the problem that might have tripped you up?
It gave us the 11 meters per second.
Yeah, so then the question is, the maximum safe speed for this car is 4.14 meters per second. What's this car doing?
Flying away.
Yeah, it's sliding way up the track, going for a trip. See, we don't need that. We don't need that velocity that we're told, because all we need to do is find the balance where the car is not going to be pulled down the track or slide up the track. Okay. This is where we're going to get into Kepler's laws of orbital motion. Okay, so let's attempt like a partial circle here. So there's your orbital path. There's a planet there. Center of mass of the planet. Then you have something maybe a moon, an artificial satellite orbiting the planet. You have your velocity there. There's your radial acceleration. Does anyone remember why I denoted the center of gravity of the planet?
That's where you measure the radius.
So if we think of Newton's universal gravitational law, gravitational force, G, 1 times 2, R squared, that R
just takes it.
Now, R is measured from center of gravity. Well, like, for example, if you're asked problems about what happens on the surface of the earth, okay, well, your R has to have the radius of the earth subtracted out. Because you are the radius, you are a distance of the radius of Earth away from the center of gravity. So then you, so the thing is to stay in orbit. When you're in orbit, you're still well within the gravitational well of the planet. Again, you're not weightless. There's actually very few parts of space where you're weightless. You'd have to be completely outside the influence of any gravitational field. And that is really, really hard to find. That's where we cross over into the realm of what's called special relativity. Special relativity is absolutely no gravity at all. General relativity is within inside of a gravitational field. Now, but you feel weightless. You remember why? Because an orbit is a what? You feel weightless, but you're not.
That's
Yes. Yeah, an orbit is a never-ending free fall. So you're out there, you imagine the astronauts doing the spacewalk, and it's like, it's okay, they're weightless. No, they're actually in free fall. If they make one little mistake and their velocity changes, they'll pull away from the space station and like a fireball straight down. Not a fun time. So then the question is, what would that velocity be that allows you to stay in orbit? Well, you have to use that understanding the gravitational field of the Earth. So let's look at that.
I hate that.
Look at the sum of our radial forces. So we can start here. So our radial force vector is going to be in the generalized r hat direction. Your r hat's always going to point towards that center of gravity. So for circular motion, which way do we say is positive? Towards the center of the circle. So since these both point that direction, okay. But then we remember your centripetal acceleration, your radial acceleration, and remember your subscript r and c are interchangeable. So remember that your radial acceleration is v squared over r. So then the first thing that you know, you can divide your mass out of both sides.
Yeah.
Now, if I multiply through
whatever cheer says.
Did I get that part here?
You were like fifth grade, so.
there, that r and that square will cancel.
You just read for like.
So that's going to give us e squared mu over r. And so the velocity you need to stay in orbit is that. Now, this ends up leading us into Kepler's actual laws. The first and second law are pretty self-explanatory. The first law is planets move around the sun in elliptical orbits where the sun is one of the foci of the elliptical. Of the ellipse. You remember you have a focus at each end of your major axis for an ellipse. Based off how football shaped the ellipse is, they'll be closer together or further out, but your star, your center of gravity has to be in one of those foci. The second law, a satellite or a planet will sweep out equal areas in equal intervals of time. So you notice there, the bigger triangle, well, it's kind of a triangle, but it has a curved side. If you're looking at that when it's closer to the planet, you're going to get a what looks like a wider area versus when the satellite's further away from the planet, you get a more thin area swept out. But the thing is they're both happening in the exact same time, and if you calculated them, they would be the exact same area. They have different arc lengths and different radii, but they'll be the same area. Kepler's third law. The square of the orbital period of a planet is proportional to the cube of the orbital semi-major axis. So basically, that's the square of the orbital period is proportional, the first symbol, to the cube of the average distance from the planet to the sun.
Inversely or versely?
Directly.
Okay. Inversely.
Versely? I've never actually heard it said
Wait,
that.
Dr. Everett, are you going to the UNMC trip?
Yes.
So we don't have class on Monday.
You don't have class on Monday, right?
No, but you're going to have a video you have to watch.
Okay.
But that video won't be on the test, right? Because we have a test
No,
next.
it will.
Oh,
We have a test when we come back from break, right?
Yep, that Thursday.
Wait, when we come
I
back
thought we
from
had a
break,
test
or when we
that-
come back from
No, when we
UNMC?
come back from the trip.
yeah,
It's next Thursday.
next Thursday.
Are you putting it on?
He's sending me so I
We
can
have
send
a
mine.
quiz tomorrow, though.
I'm just doing mine on
Putting the
paper and
video
like
on
email
YouTube?
it.
Yeah.
You remember last time? It just was, okay,
Yeah.
thank you.
But you don't
Don't
have
worry.
an hour and 20 minutes again, right?
Depends on what we have to get through.
You can't do that. Because I have to take a genetics test on Wednesday too. I do first. I have to take anatomy
So let's think about this.
I think I take anatomy at.
What do we already know?
I think we take, do you think we take biochemistry?
What if we send our teacher out
Because
the
I'll take
bus?
my genetics test.
the way normal?
Whoa, yeah.
And then
Well,
we'll have
we
to
can-
take
we
a
can
test?
flip it, you know. Whatever works best.
Actually, I'm going to be out of reach of most of you for the entire trip.
Don't worry, you'll be back in reach once we get to.
Don't worry, we'll find you. Don't you fear.
Best of luck, because I'm going to be in Lincoln.
Threat.
I know,
That's only for a day.
You meet in Kearney.
Yeah,
You're taking the dental kids to Lincoln?
Huh?
The dental kids get to go to Lincoln this
Yeah.
year? I
On
hate
Sunday
them.
night, on
So-
Sunday night.
I hate them.
The bus is going to stop in Lincoln and drop off the dental people, and then you all, the rest of you are.
They're gonna spend all day there?
And you'll have to ride back.
Dude.
But we literally got 2 hours there my freshman year, and we didn't even get to go there last year because they were doing renovations.
What do you do?
We hung out with.
We hung out in a room.
What else do we know?
Yeah.
No? Velocity
But it's only.
I'm gonna throw a cat at you.
is the rate of change of position in circular motion. What is S over T? How does delta R over delta T relate to S over T? Change in distance, which is your time for a full revolution.
Yeah, Everett, we'll figure out which room number you store. We'll just knock on every door. Correct. No, you'll hear us.
Oh, yeah. You're tempting me to bring one of the power supplies from the physics closet, plug it into my room, turn it on, hook it up to the doorknob.
Like you cute us.
No.
That sounds like a threat.
As long as it's 0.3 amps or under, you're just gonna fill up.
Like a hot wire.
You know what's funny about Gillette?
Wait, you touch one?
Yeah, so
Yeah,
don't
like
find
that.
Everett. So I'll just bring my gloves. No.
So we can set these equal to each other.
Best limit line and it's different. He's.
Talks a lot. I just listen.
You can tell though, there's like a big difference.
I listen
between
too
him.
much.
You put one finger on top. You're really gone.
So now we can start solving.
I think it's.
That was good news.
Some people
No,
don't.
that's not.
We laughed at
No,
it.
yeah, it's all my
You
theory.
did not hear what he said.
Burger.
No, don't take that back.
You just gotta rush in the crap out of burger. Sure, I did.
You guys remember how to take a square of a whole thing and bring it inside?
It's game planning.
I don't know, but you keep making me do it.
That's one of the most basic things. You don't know that. If you don't know that, you should retake college algebra before you think about medical school.
That's probably.
When do I need to do math?
Yeah,
Is
why do I
it-
need to do that with teeth?
You're lucky. I don't.
Okay, so we can multiply through on one side, we're gonna get t squared.
And this is actually directly after. Oh, right, yes.
Just like
Equals,
this, like.
when I multiply the r,
Standing there like.
this side, what do I get? Yep.
Just left.
4 pi squared r cubed,
Like.
and we can end up at t squared. is going to be
He's like the guy that do like.
Hey, that's a little class.
Yeah.
Is that R cubed?
Yep,
There you go. That's a little kidding.
Help me get that.
The only math I'm doing is.
over g mass of the earth,
Yeah, I didn't think of that.
which we can factor out.
Yep.
You multiplied the R.
Huh?
Oh, I see.
He doesn't punch, he just sticks in there.
So we get here. And so what you notice is that, yes, in fact, t squared is proportional to r cubed with, and so again, what do we have to take something from a proportionality to an equals?
The other fish.
No, not the other, constant.
Why is the fish going that way if it's directly proportional? Yeah, it needs to be flipped.
No, it doesn't.
Yeah, the fish swims the right way for directly.
Does it?
Yeah.
I don't know.
Well, I thought we looked it up and you said like it can go either way.
You just have to like be consistent with it, so now you're inconsistent. Cause you did it the other way on the other
Did
side.
I do it the other way? Like that? I don't think I did, but if you're comfortable with that, whatever.
Thank you.
Wait, sorry.
The whole thing is your period squared is directly proportional to your r cubed. For proportionality to become equal, you have to have a proportionality constant. So your t squared has to equal some constant times r cubed for it to be equal. And so our constant in this case
Stop. I don't. We're giggling.
So that whole thing is your constant. Like next semester, you're gonna find that the Coulombic force law is proportional. And the proportionality constant is, you can either like, sometimes you see textbooks write it as a K, and it's 1/4 pi epsilon 0. And so that'll be a fun new constant for you. The epsilon 0 is the permittivity of a vacuum. The But this proves Kepler's third law. So let's say a lunar lander is orbiting the moon. If the radius of its orbit is 1/3 the radius of Earth, what is the period of its orbit?
Let me see.
Well,
Mechanics I'd be doing is KSP.
the first thing to think of,
Don't bring that up. They were talking about KSP.
Me too.
No.
we can start with
Why I remember that. Which constant is that? Is that precipitation?
Yes.
Yeah. KSP is precipitation constant. There's a few, there's like 4 different constants. Yeah, that are like.
Yeah, you have to.
so we can start there. What did I change?
You swear it, that little M.
Little m. What's the little m?
Yeah, yeah.
Moon.
Yeah.
I'm orbiting the moon. I have to worry about the mass of the moon. I need something for r, and I need it to be a number that I know. R is going to equal what? No problem. R equals.
Radius.
Math issue.
1/3 the radius.
1/3 the radius of the Earth.
Yeah.
The R itself is the position of the satellite in orbit, from the center of mass of the moon out to where it's orbiting. But that orbital distance is 1/3 the radius of the Earth. Okay?
It's not. It's not.
It's supposed to be him. To be him. Yeah. It could be like distraction. You'd be like, hey, quite a drill, a little bit after practice. Wait, let's go spike over there. That's what you did.
Which I can change to,
I should walk in with him.
see how well you guys remember fractions. What is 1/3 cubed?
One.
Oh, that's squared.
Oh,
127?
127?
Yep, 127. And then, what numbers do we have to find?
A, B, C, and D.
What numbers do I have to find that I should be able to find without having them written in the problem?
Just dead R, I mean,
And G, the gravitational constant. So G is,
Really? She got you on that one?
I know.
With Tim.
Me about.
With Timmy Tim.
Earth. Where do you think I find these at?
books,
Where?
in a table.
Where?
At the back. Page 75.
Not even close.
In the back.
Appendix 2.
Was that in the back?
Yes. And again, saying in the back is like me saying, what's the square root of 81? And you're like,
Nine.
9.
Like, yeah, you.
At least, yeah, it's somewhere in the ballpark. No, you
But is that wrong? Is 9 wrong?
cannot answer a question with, it's at least this.
Then why can't I?
Like if I asked you for a velocity, you said it's at least 5 meters per second, that's gonna be a big no.
I don't understand. I never said literally, I said in the back, I said in the back. of the
I said,
book.
well, and saying that is the same thing. In the back of the book, what do you mean by the back? Is that back halfway? Is that the last 100 pages?
I can't figure out you got it.
You speak equivocally, no one can figure it out. Now, put these numbers in and see if you get
About me?
Yeah, no, I just think,
You have to.
like, if I don't.
You can get that number.
Why am I staying? You tell
That's what I'm
me
supposed to do.
something like,
Mhm.
that's rated. Oh, I forgot in 2 seconds.
Exactly.
I don't know what to say.
So just
So make
say.
sure you're practicing how to use the pie button.
I love the pie button.
About me? Oh.
We only don't like you.
I'm just.
So anxious.
He just doesn't like these.
I can't wait till next semester when you guys find out that on the Earth, the North Pole is the South Pole.
No.
That ruins scientific work.
Say that one more time.
I have a question.
That on Earth, the North Pole is the South Pole.
I have a question. How did they figure out the radius of the moon and the mass? Seems pretty fake to me.
Doing a lot of calculations like this, like they can watch the orbit, they can measure it. Like, for example, they watch the telescopes, map out an arc length.
You actually.
Secondary location. Just can't help yourself, can you?
So remember, a lot of these guys, a lot of these people lived in a day where there were not copious ways to distract yourself. So now we have all kinds of ways to have fun and distract ourselves. Like Isaac Newton during the plague, he had two choices: stare at the wall or come up with physics.
I would have too, honestly.
Yeah. Yeah.
I would have been
No, you make fun
Yeah?
of. I'm ready. What? He's just insulting us.
Is it?
He's anti-feminist.
Let's see, I've been to Louisville, so I think I'm gonna stumble into that minefield.
That's literally not.
No, it is.
I've been misogynistic.
All the better to match your misandry.
Yep, basically. I stand by that. I know what that word means.
Do you?
I do. It's like misogynistic, but for men. And or as men.
You could say they're inversely proportional.
Finish. Definitely not versely.
Just because someone is their view, someone thinks.
Uses their vowel.
You know, get the number? Nice.
I didn't.
That's gotta be a rounded answer.
Been a long time coming.
No.
Is on the one where it says like art, is it still cute?
That means
Now,
Having art.
we've been talking about uniform circular motion.
You've been insulting us.
Let's move on to non-uniform circular motion, which means what?
Squares.
Yeah. Just say it
It
feels.
is. What's changing as you're orbiting, as you're going around in a circle? So you remember all those little velocity vectors you drew that are based on the circle at each individual point?
I'm like, no,
Look at my actions.
So,
No, I heard that.
in general, so let's say we have a circle here, part of a circle.
I'm just gonna do, let's do that.
Say.
Oh, no. I don't think that's exactly the center of curvature, but it's there. And so for each one of these,
With that thing, okay, let's play this.
we have our two velocities, V1 and V2. So what do you think we're gonna have to do with these? What is this? Mhm. Now, this is kind of a generalized expression. You'll find in a little bit that we're going to use this delta V for tangential velocity, but what this is going to show you, your delta V points in the direction of what? What also points in the direction of delta V?
Oh, I don't know. At least like.
Total acceleration points in the same direction as delta V. So now imagine, that means you're going to have, just do it over there. If we take that and go back around the circle, let's draw another circle.
She was dead. She was in the car.
Just a certain smell.
Okay, so if we take this delta V,
So like they can see this.
Don't smell bad. It's not a bad smell. It is a weird kind of cookie. Like an interesting kind of sanitize. Hospital.
delta V is going to point in that direction. And so that's also going to be your radial acceleration. So it's going to point in that direction.
That's a romantic.
But this radial acceleration is in 2 dimensions. Which means you're going to have,
Wasn't it you?
No, it wasn't. It was someone. Between you two.
It was definitely you walking in and something smelled like oil.
oh, sorry, this is not radial, that's just acceleration.
Yeah, I'm
The
sure.
radial acceleration is there,
I think it's going insane. Every time I look up here, the.
and your
it's like-
tangential acceleration is there. So the point is now you're getting these accelerations where your two components now are your tangential acceleration and your radial acceleration. So instead of x and y, you have components of tangential and radial.
What's
I don't know what that means.
what's the T one?
Tangential,
Yeah, what's that mean?
what is a tangent to a curve?
Great question. Opposite over something. Something over something.
Sine over cosine.
No,
Yes, that's what I meant. Oh,
It's tangent to a curve, not just
a
tangent.
tangent to a curve is like this. What is it doing?
Going around the curve. At one point.
It is a straight line that touches your curve at a singular point. That's why when we get the instantaneous velocity and rotational motion, it's a tangent.
What's my regular? You sure?
Radial-
Your regular tangent is the.
Are you talking about an angle? That's sine over cosine. The tangent to a curve is a straight line that touches the curve at a singular point, which is another thing that completely defeats the argument of flat earthers. So like, I look at it and I see flat. You see it differential of the curve. That's it. If you can't tell me what that means,
Can't use this. I enjoyed this one. That's my number 2. I'm so shy.